This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. In the last lecture, we started this combined cycle problem. So, as mentioned, the combined cycle is the a steam power cycle combined with a gas turbine power cycle. So, essentially, the two cycles for this particular problem are all running on their basic design, and they coupled through this heat exchanger, which is used as the steam generator for the steam cycle. So there we already solved part of the problem, where we find that for the gas turbine part, we solve the net work for the gas turbine, which is equals to 275 kilojoule per kilogram of air. So all the energy term we deal with in our psychoanalysis is mass specific, right? The mass specific is the specific mass that is being normalized for all those energy terms. That is for that working fluid. So for the gas turbine cycle, the working fluid is air. So the mass being specific by, that's for the air, which is the working fluid. All right, different cycle has different working fluid. Then the mass specific corresponding to different physical meaning. So that's actually one of the point being examined here to test your understanding of the physical significance of those concepts. All right, so here we have the gas turbine cycle. Then we need to find out the work for the steam turbine process as well. So there, let's use the conditions given. We need to find the work for net work from the steam turbine. So let's starting from the statistics, which is a pump inlet. So there we know that the pressure there is 20 kPa. And we know that it's on the saturation dome, which means its quantity, steam quantity is 0 there. So based on these two, you can just go to the table to find the H6, the enthalpy, which is equals to 251 kilojoule per kilogram of working fluid for this cycle, which is steam or water. It doesn't matter. It's a different working fluid compared to the air. But it's mass-based. It doesn't matter whether it's a vapor or liquid. So you go to, as mentioned, there is different tables. For water, in particular, you have 3 tables. You have saturation table, which dealing with all the properties underneath saturation dome, including the dome. You have superheated table, which is on the right-hand side, and the compressed liquid, which is on the left-hand side. the compressed liquid table not available for all the liquids, but because water is very common, so it's already being available there. So we have H6. Then if we want to find H7, we can go through this isentropic process to find the state, but what we really after is the work. So we know that the pump work can be written as the specific volume, which is V6, and the pressure difference P7, P6. So the V6 is coming from the state 6. So the V6 equals 1.02 times 10 to the minus 3 meter cubic per kilogram. So the specific volume of water is a pretty small value, you can see. And then you bring it there, and this value, the pressure is 6 megapascal. And this one is 20 kPa, so it's 20 times 10 to the 3 Pascal. Here you need to use the Pascal and the meter cubic per kilogram. So the one good habit you want to develop in doing the thermodynamic calculation is you convert everything to the metric unit. All right. So that will give you, then during the calculation, you will end up with metric unit. What are the metric unit? For length, it's meter, not centimeter, not millimeter. For weight, or the mass will be kilogram, right? And for the volume, that will be cubic meter, not the centimeter, not other things. So if you and for pressure, that's the Pascal, not megapascal. So you convert everything to the basic metric unit, then you end up with the joule, end up with watts. So don't dealing with the kilojoule, kilowatts. I mean, if you really know how to do it, then that's fine. But the safest way is just dealing everything with the basic unit. All right. So with that, I can calculate the pumping work, which is 6.1 kilojoule per kilogram of the steam again. So it's a pretty small value, just because the specific volume of liquid water is very small. All right, so then we can find the H7. H7 can be obtained from H6 plus the pumping work. And then we have the 257 kilojoule per kilogram. All right, then what we really after is 8 to 9 step, right? So we want to calculate the 7 because 7 later on will be used for another step in the later calculation. But what we really after is a turbine work, which is from 8 to 9. So let's figure out state 8. From state 8, we know that state 8 actually is a given. The pressure is 6 megapascal, and the temperature is 325 degrees C. So that's given in the problem. Given in the problem. So then we just go to the superheated table to find the enthalpy there, which is 2965 kilojoule per kilogram. All right, so that's the state 8, superheated steam. And then we want to figure out state 9. And state 9, how do we know state 9? Entropy, so which means we need to figure out the entropy at the state 8 first, right? So state 8 would be 6.203 kilojoule per kilogram and per Kelvin. Right? So state 9 has the same entropy as state 8, and also state 9 is say it again? It's a mixture, so should have basically the pressure and temperature is known because it's on this horizontal line, right? So how do we do this? What's the next step, basically? Find the actual entropy. Entropy already known here. From the table, yeah. So there, and then what's next? You know this state. Find the quantity. Yeah, find x. And how do we find x? X 9. So I listed an equation before in terms of how to find the quantity. Find the quantity, you need to know that's the next step. That's the important thing. And then you need to remember what's the equation to find the quantity here. So there, if you recall the equation we have before, there will be S9 minus SF and SG minus SF, right? That's the entropy there, which is SG. Entropy there will be SF. That's all from the table. Then with the known value of the state 9, you can figure out the quantity there. So that will be 0.7 59. Right. That's the step you must know well. Yep.
Is that right? Because it's usually over 88%.
Yeah. So in reality, in practice, this value is low. You want something around 88 or even 90. But that's this problem is given to you, and but if you notice that what we discussed here, the actual process is not isentropic, right? What we figure out is the isentropic process, which is a vertical line going down, and what we need to figure out is this actual state, right? So we need to consider that the turbine inefficiency, all right? How do we do that? Let me put this OS. This is O for the isentropic process. We write the turbine efficiency, right? The turbine efficiency is defined based on the ratio which is containing the isentropic process and the actual process. So if you consider turbine efficiency, that will be H8 minus H9 actual divided by H8 minus H9s. And this value is given as 0.9. Then you can figure out the H98, right? And that's given you a value of 2132 kilojoule per kilogram. Again, that's steam. So we take into account the turbine isentropic efficiency there. And if you check this value will give you a quantity if you bring this value to check the quantity, so in other words, if you check x, 9a will equals to h9 a h f hg minus hf. This value again is from the table that's smaller than 1. So which means we are still under this saturation dome. So we are still here. We are not getting to the overheated zone. All right. So what we really need is the enthalpy, which means what we really need is the enthalpy difference so that we can determine the turbine work. So the turbine work can be obtained, or maybe I write the net of the steam turbine is the turbine work minus the pumping work. So that will be H8 minus H9A, the turbine work minus the pumping work. So we figured everything there. So I just give you the total number. So that's 825 kilojoule per kilogram steam. All right, so we achieve the basically that's the preliminary targets to figure out the net work that is being produced by each of these cycle. What we really need is to determine the combined cycle, right? So for the combined cycle, we mentioned that the power can be written as the net work produced by the gas turbine times the mass airflow rate of the gas turbine, and plus the net work produced by the steam turbine and the mass flow rate of the steam going through the turbine cycle or steam cycle. Right? So we figured this, and this is what the problem is asking. And this one is known, is 100 megawatts value. So we figure out this, but we don't know this. So the problem essentially is asking you what's the relation, or can we find this steam flow rate as a function of the air flow rate? So that's the next step. If we figure out that, then we solve the problem. Right? So how do we, any idea in terms of connecting these two? Yep. Very good. So these two are coupled together, and the problem says it's a perfectly insulated, which means energy transfer there is perfect. No heat loss. All the energy that is lost by the gas turbine exhaust goes into the steam turbine cycle. All right? So that's an important link between these two cycles. So if we have consider the energy balance at the heat exchanger. We call it as a heat exchanger, but in practice it has a more specific name. It's called heat recovery steam generator. Or HRSG is its acronym. So there we have the total heat which is coming from the GT in its absolute value equals to the heat received from the steam turbine. So that's an important link, and again, we do not necessarily teach this in this subject, but one of the primary purpose for you to learn thermodynamics is you know how to conduct the energy balance for a given system. All right. Basically, that's the energy balance is the first law. Right? First law can appear to be very simple, but you need to know how to apply it to different systems. Sometimes it's not that straightforward. So if you're aware of that, then it's pretty straightforward. You have the air, Cp, T. So there we have the heat that being lost from the exhaust. That will be 4A minus 5. So T 4A minus T5 then equals to the steam side. We have the H 8 minus H7. So all these values should be T5 minus T. Yep. Yep. So just by doing this, you have these values that's being figured out. Then you can determine that the M air versus the M steam is something around 10 to 1. All right. So then if you consider this equation there, then we can just bring this as a function of the mass flow of air. So we have 100 megawatts that equals to the value that we obtained. From 275 kilogram per kilogram air, kilojoule per kilogram air. All right, I should write in the standard unit. Then times the m dot air and the times the work that we figure out from the steam turbine, that will be 825 times 10 to the 3, then the joule per kilogram of steam. And then divide by 10. And then times the mass flow rate of the air. So basically the idea is you cannot add the two work term together. The steam term needs to be converted or discounted so that to be equivalent to the gas turbine work. All right. So then we can find the air. Mass flow rate of air is value 279.2 kilogram per second. So this is a 279, all right. So this is a huge, huge amount. If you consider the density of air is about 1 kilogram per cubic meter. So this is about 280 cubic meter of air coming in per second. So 280 cubic meter is about, if you have 3 meter by 3 meter area, so 3 meter is about, I would say, somewhere over there, 3 by 3. Then you have 30 meter long of this area. They're coming into the engine per second. So that's a huge amount of air. And as we said, if you want to run the combined cycle, you need a very large gas turbine to drive a relatively small steam turbine. right? And this often is not being achieved by one unit. You can have multiple gas turbines running together to drive a steam turbine. All right, so that's the second part. And if you recall, the third part is asking what is the efficiency for this combined cycle. So that can be calculated. So combined cycle efficiency, again, is work output or useful output, which is work in this case, and the required input. So if I have the gas turbine plus the steam turbine and the total heat input, so if I have 275 plus 825 and divided by the Cp, the Q in. We didn't dealing with Q in till now. What is the Q in of this process? Said T3 minus T2A. That's it. Just the temperature. Cp, right? Yeah, T3 minus T2A. All right, so Cp is given is about 1.005 kilojoule per kilogram per Kelvin. So I have kilojoule all there. And then times the T3 is 1373, 1100 degrees Celsius. And the T2A is 573. All right, so if I do the calculation, so this is 800 times 1 is about 800. So these two add up to be 1100 divided by 800. So I got something over 100. So if you add these two, that's 1100, right? And this is 800 times 1, right? So that's 800. What's I did something not right? What's that? Pumping work is considered as part of the steam turbine cycle, so it's already considered there. So that's okay. I don't have it, but it's considered. And pumping work, I should say, if you're looking at this is the pumping work that we calculated, it's about 6 kilojoule compared to the energy term there. That's nothing, right? We said the pumping work is very small in the overall cycle. So even we don't consider the pumping work, that's not a problem. What's the problem here? So these two cannot be directly added together, right? So this one is, again, the kilojoule per kilogram of air. And this Q in is based on the gas turbine cycle. That's also kilojoule per kilogram of air input, heat input. This one is we calculate directly from the steam cycle. That's kilojoule per kilogram of steam, right? So that these two cannot be added together, even though that's a kilojoule per kilogram, but that's different kilogram being normalized too. So this one needs to times the mass flow rate ratio of the air and the steam. So which we figure out that's 1 over 10. So then that's a reasonable number. So then that's wrong. If we consider that one time divided by 10, we'll end up with 44.5%. All right, so that's a reasonable number for as a thermal efficiency. So in fact, we consider normalize the steam turbine work in the step right above it. But since you didn't go through that process yourself, you didn't really have a deep impression on that. And here, don't be caught by the problem again. All right, so if you recall this value, and this value actually is pretty lower compared to the highest efficiency in reality. So we said for combined cycle, it can reach very high efficiency, over 60%. But here, we do not reach that. And any explanation in terms of why that? We already consider ideal cycle in most cases. There is no heat loss during the combustor. There is no heat loss during this heat exchange process. So heat loss already been minimized in our problem, and also the inefficiency 85% for the compressor and 90% for this steam turbine and gas turbine. That's not too low. So those are the practical numbers. So why we end up with a lower efficiency than the reality, right? We would say the reality probably cannot reach the efficiency of ideal cycle. If the question asking you to discuss this, what are the parameters controlling the efficiency for the gas turbine and the steam turbine? Temperature, inlet temperature of the gas turbine and the steam turbine. That's the value directly control the efficiency, and that's the value has been reached nearly the maximum, or at least the maximum we can reach at the moment. All right. If you looking at the value we use here, this one is only 1100 C. We said in reality you can reach 1600 degrees C. So 500 above this value. And also, this is the primary reason, because this is driving the whole thing. And for this steam side, steam turbine, we said in reality you can reach 620 or at least 600 degrees C. And we didn't reach that value. So these two temperature, which is directly control the efficiency, is not being used. We didn't use the maximum value there. So that's directly control the overall efficiency. Even we consider there is no heat loss in the cycle. All right, so less than 60% due to the T3 is smaller than 1600 C, and the T8 is smaller than 600 degrees C. All right, so I think that's all for this problem. Yep. So that's basically the end of the psychoanalysis. If there are no questions, I want to have a quick review of this part, and then we move on to the next big topic, which is the heat transfer here. All right. So let's have a quick review or summary. I mentioned before that the psychoanalysis is very simple. It's inherently simple in terms of calculation. That's all very simple algebraic equation. And the only trick thing is you need to understand how the process goes and how to apply the basic relation to the process. And in solving this problem, the primary tool we use, whether you are aware or not, we apply the first law. We always apply the first law as a first step, and we always apply the state postulate, whether it's a gas power cycle or the vapor cycle. We always apply these two, because these two, first law is always there, and the state postulate applies to the simple compressible system that we're dealing with here. So you know two independent intensive properties, you can, the system, that state is known for the system. Then you can find the rest using different ways. So other than that, when we're dealing with gas cycles, gas cycle is being called gas cycle because the working fluid is ideal gas, and we have additional tools to solve the problem. Ideal gas law and the isentropic relation. Isentropic relation, if you recall, that's coming from the Gibbs equation, and Gibbs equation is a combination of the first law and second law. So these two can be used for the gas cycle to solve the problem. And if we're dealing with the vapor cycles, the calculation is even less, but you need to go to the property tables to find out things. Just make sure you use the right property table. And often if you using the wrong property table, you cannot find the number, because that state is not exist on that table. That actually is a reminder that you need to go to a different table. So the calculation here is a very very simple. And in terms of understanding, that's also not very difficult, as long as you know how the process goes step by step. Right? If you're looking at the 3 cycle, basically we discussed 3 cycle, but for most practical cycles, that's more or less the same. The 3 cycles, which is the Brayton gas turbine cycle, which including Brayton and the turbojet, they have almost the same TS diagram, and the refrigeration cycle and the steam power cycle. So for all of these 3 types, we're dealing with multiple states, multiple temperature, but we're always dealing with only 2 pressures. In all the 3 cycles, we're only dealing with, I should say the basic cycle, we're only dealing with 2 pressures. If you have a intercooler or the reheater, you may have more pressure. But the basic cycle, we're only dealing with 2 pressures. So understand that that's useful, because temperature, there is many, can be complicating, but only 2 pressures. One is corresponding to the pressure at the hot reservoir, and the other at the cold reservoir. And the device that allowing us to jump between this jump up and jump down at these pressures is just a few devices. That's including compressor. So opposite the compressor is a turbine. And we have pump. And we have diffuser. With diffuser, we have nozzle. And we also have the throttle valve. So these are the devices that increasing the pressure. And these are the device which is decreasing pressure. Right? And within them, actually 5 of them is we can apply the isentropic process to it. Except the throttle valve. Throttle valve, we said, is isentropic. The entropy conserved across the throttling valve. But for the other process, we can apply the isentropic process. Not necessarily isentropic law, because if you're dealing with steam turbine, you are not necessarily applying the isentropic law because you are not dealing with ideal gas. But the process can be considered isentropic on the TS diagram, which you have vertical line going down. All right, so that's pretty much it for a quick review. So different cycles, we discussed the different ways to modify it, to improve it, making it more efficient, or making it producing more work for a given size of engine. So those are the things that actually is new in this subject compared to the things you have learned before. And that's also where those tutorial problem, assignment problem, and the exam problem will be about. All right. So with that, I conclude the psychoanalysis part. So let's move to the next topic, which we will spend the rest of the semester to discuss, which is a heat transfer. Heat transfer is a very important discipline or topic in the thermodynamics, and the topic, or this topic, is mainly concerning a rate. So it's concerning how thermal energy is being transferred in terms of how fast or how slow the process is. So the rate of thermal energy transferred between a system and its surroundings. So rate is a different concept compared to we learned in cycles. So in cycle, we almost dealing with no rate. So we said from state A to state B, certain energy being transferred. We didn't know how long that process happens, right? So in the last example, in the example we demonstrated, we have the power generation term involved that bring in the airflow rate. So that bring in a little bit of rate, but in all the discussion we have, we didn't care how fast the cycle runs. We just say from here to there, how much energy is transferred from the start to the end. We don't dealing with rate, but the rate is a very important in practice. All right. So what we are going to discuss is basically the how the heat is transferred, which is happening in three modes. We can quickly go through it, and the main concern is how the heat is or thermal energy is transferred through these three modes. For each of three modes, there is a rate equation to describe it, describe the heat transfer through that mode, and then that's things we are going to study, spend most of the time to learn and to apply. So let's look at the three heat transfer mode quickly. That is known to date, three modes. One mode is called conduction. Conduction, we consider that if you have like solid, or which has two surfaces, and each surface has different temperature, then the heat will be transferred by nature from the hot to the cold side. So your simplest way is you have a surface or you have a wall, for example. You have temperature there as T1, temperature there as T2. Then the heat, if this is a temperature gradient, then the heat will transfer in that direction. So that happens by nature. So that's process called conduction. If you have a solid that can two surfaces at different temperature, that can happen. Or if it's air, so if you consider a certain type of double glazed window, which has a glass on both sides and has a layer of air being sealed in between, that air is not moving. Right? The important thing is the air is not moving and just work like a solid, except it has lower density. In that case, you have different temperature, the heat will also transfer through. So that's different from convection, which is a second mode. The convection involving a flowing or moving fluid. So in this case, for example, you have a surface, and you have which is solid, then you have a flow coming in. For example, this is a surface outside, the air is blowing. So the air or the fluid has a free stream temperature, and that's different from the surface temperature. If the surface is hotter, then the heat will transfer in that way. And that's called convection, which is involving moving fluid. The fluid must be moving in order for the convection to happen. So if the fluid is not moving, you can have conduction happens. Right? So that's the second one. Then you have the radiation. Radiation is a third mode, and it's actually quite different from the first two. The radiation heat transfer example is if we have the sun outside, right? If we have if this is Earth and we have a surface on Earth, the heat will transfer by thermal radiation from the sun to the any surface on Earth. So this mode is called radiation, and in fact the mechanism is very different. In this case, the heat is transferred as a same mechanism as light. It's as an electromagnetic wave coming from the source to the targeted surface. Examples of heat transfer is many, as many as you can think. In fact, so here is a few examples, which is actually included in the lecture notes. Commonly used in industry, which is a heat exchanger. So this is one type called shear and tube heat exchanger, which we will study later on when we study the convection part. So you have fluid, one fluid going in the green region, which is the tube flow, and then going this way and then coming back and leaving here. You have another stream of flow which is coming in the shear side, which is outside the tube, then in the light blue, then going there and leaving there. So this is commonly used in industry if you want to recover certain heat, or you want to cool certain fluid, or you want to heat certain fluid. So you have them have heat exchanger. In fact, that can save energy. And also to heat or cool the stream that you want to be cooled or heated more efficiently. All right. So this is a device in a desktop computer. So there you would have, I should say, in this heat exchanger, in terms of the heat transfer mode we discussed, it's mainly through convection. But it's multiple mode being combined together. You have the convection for the external flow or the tube flow and the shear flow, but also the heat is conducted through the tube wall, which is a conduction process. So for this device, or I think this is a fan on the desktop computer. So there you're mainly dealing with conduction, which heat is being conducted off the CPU or the electronic component which is generating heat, and then through convection, which is a fan bringing air to dissipate the heat away. And this is a combustion engine. This is a piston engine, and this is a gas turbine. So for combustion engine, the important task is to cool, because the temperature is so high. If you don't take the heat away, then the temperature can melt the metal. So an important task is to cool them, and both conduction and convection are involved in here. Another two examples actually, which is related to the human comfort. So as a human, we are constantly generating heat. So the base of production is about 90 watts. So everybody is generating this much heat. That's why if the room is full, it's a lot warmer compared to empty room. And this amount of heat needs to be constantly dissipated in order for us to feel comfortable. So if the outside temperature is higher than our body temperature, if it's 45 degrees C compared to our body temperature, then the heat is difficult to be removed, right? And in that case, the effective way to keep us cool is sweat, right? So that's basically you're using the evaporation cooling. So when the water is being converted to vapor, it will absorb a lot of heat in order to keep our body temperature at a normal condition. So this is an example of the radiation, and particularly it's the solar radiation. And what's showing here is the solar panel, which directly converts the radiation to electricity. But in many cases, you can also convert that radiation to heat. You can use that to heat water. And actually, the solar energy is a very large amount. The energy that is received by Earth's surface in 1 hour is enough for the entire world to run for a year. So the solar energy is enormous, but the main problem is it's too diffused. The energy density or power density coming in is too low. It's difficult to collect them and use them. But if we find a good way, then that's certainly can solve our energy problem. All right, so that's all for today. Let's continue Friday.
Yeah? I don't understand this. How does this come? How does it become, how does facial form?
So that's coming from the calculation there.
Oh, from the calculation. They're substituting the values of this and getting
Yeah.
in terms of mass approach, air approach.
Yeah. So that's based on the energy balance between the two streams.
Yeah, okay. So in that heat exchanger.
Yeah. I think I put it there.
So I got a problem about the gas turbine. So a normal gas turbine is got a TS diagram like this one. And this is the inlet temperature of the turbine. This is outlet temperature of the turbine.
Yeah.
So we get this equation. But if there's the turbojet, like if I add a nozzle behind the turbine, this the temperature 5 is the temperature of the nozzle. So is this equation becomes T2 over T1 equals to T3 over T5.
Yeah. So if you want to direct, are you saying you want to directly apply from T3 to T5?
Yeah.
Or just the T3 to T4?
Is this correct? Like
T2.
T2, in this diagram, T2 over T1 equals to T3 over T5.
Yes, if you're using everything as a stagnation property.
If this whole process is ideal.